And so my research area is in security and privacy and crypto. So for me, actually, I was trained like a sort of like a cryptographer. So I knew cryptography first before I knew cryptocurrency. And like the first time I got to know cryptocurrency was like back in 2011. And I was very fascinated by Bitcoin, and like my collaborators and we kind of wrote the first academic paper that tried to introduce like cryptocurrency to the academic community. And this was the Bitter to Better paper. So I'm a little unprepared for this session. So like 5 minutes before the session, I wrote down several directions and thought this might be useful to help kick off the discussion. So here are some of the exciting directions that cryptocurrency poses for the cryptographers. First, obviously, you know, one very important question is how can we design provably secure cryptocurrency, and essentially how can we design provably secure Byzantine fault tolerance protocols, consensus protocols, and from there we also want to bootstrap provably secure applications on top, and in particular smart contract applications. Okay, so one thing about this that is different from traditional cryptography is that typically in traditional cryptography, one of the standard assumptions is, let's say, honest majority, or maybe that the 2/3 of the network behave honestly. But in a cryptocurrency environment, as we all know, people behave selfishly. So I think that's like a very important difference from the traditional cryptography. Okay, so the second thing that crypto may be able to do for cryptocurrency is to increase the privacy and anonymity, for instance, anonymity of for user identities, to hide what transactions and the amount of transactions you might be performing, and maybe also to hide what kind of contracts are running. So as we all know, the blockchain is kind of like a public bulletin board where everyone can see the contents of the blockchain. So if you want to have these additional privacy guarantees, which in many applications may be desirable, like, you know, maybe you don't want people to see what kind of transactions, what kind of financial contracts you have with other companies, right? So in this case, we may need cryptographic constructs like commitments, let's say secure multi-party computation. There's a lot of recent developments in crypto, especially in the secure multi-party computation world, where you can have, you know, close to practical protocols. And there's also a lot of exciting developments in the theoretical crypto community that looks at things like functional encryption, predicate encryption, fully homomorphic encryption, program obfuscation. And these are a little bit far from practice today, but you know, I think they are fascinating nevertheless. Okay, and then also it would be interesting to consider how to leverage cryptography, like maybe things like snarks, to increase maybe the scalability of the blockchain. So maybe this problem was also discussed earlier in the morning sessions. Maybe the miners can verify the blockchain just by doing some very efficient computation, like using snarks and verifiable computation. Okay. So this crypto plus programming language is a very exciting area. So we've been doing a lot of work in this space. I'm not going to mention too much in this session because actually in the afternoon there's this formal verification session, and I'm also going to give a talk on this experience we gained in our undergrad cryptocurrency lab. So I'll elaborate on this more in the afternoon. And essentially the high-level idea is we want developers to be able to program very easily, you know, without having to worry about how to construct the cryptographic protocols. So ideally, these cryptographic protocols can be generated in an automated fashion while ensuring formal security. Okay, and then finally, this is kind of like a very big area. In cryptocurrency, you know, we've been discussing topics related to game theory, modeling incentives, and economics. So how do you kind of combine these different areas to kind of, it's also basically related to the first point, right? So if we want to have provable guarantees for cryptocurrency, we actually have to consider the users as maybe being rational instead of honest. So I think this is, there's a lot of fascinating research topics in this area, and a lot of it is still kind of unknown. Like, I think it requires interactions between, let's say, cryptographers and economists to make progress on these topics. Okay.
So, should we introduce ourselves, start the panel off? I mean, I've already been on a couple panels, chief scientist, founder of the Ethereum project.
Developing a cryptocurrency called Pebble, which is using new combinations of Byzantine fault tolerance and cryptography. And Elaine, you already know.
Yeah, I already.
Yeah. So I guess the point of this panel is originally to try to discuss some of the various different innovations that we've been seeing in pure cryptography in the past 10 years, 5 years. Some of the really spooky stuff like program obfuscation and zero knowledge snarks, and see maybe what the interplay between those and cryptocurrency could be. So.
I think it's the possible synergies between cryptocurrency and cryptography. You might not expect it, but I think they're only just beginning to be explored. I'll give you an example. My system uses a synchronous randomized Byzantine fault-tolerant consensus protocol, which needs something called a common coin. And again, the common coin is nothing to do with cryptocurrency. It's a common source of randomness, which the nodes use to bring themselves to consensus. So to make this protocol work, you need this thing called a common coin, which is a common source of randomness. And I spent a long time trying to work out how I could create a cryptographically secure common source of randomness. And of course, it wasn't something I could do, so I spent time looking at the cryptography papers out there. And in the end, I found a paper that had come out this year it was a thing called a linearly homomorphic structure preserving threshold signature. And a threshold signature is a thing where each party creates only part of the signature, right? And from those parts of the signature, you can create the whole signature. And this particular algorithm was deterministic. So I realized it's like a sort of shared hash function or something like that. Some proportion of the nodes can produce, some subset of the nodes can produce their signature shares, and any two subsets will always produce the same signature, so long as there's a sufficient number of nodes in these subsets. And the other great thing with this algorithm was that the nodes could calculate their signature shares, their key shares, in a distributed manner. It didn't need a trusted dealer. They could perform this protocol. They could meet on the internet, right? And they could perform this protocol, and they'd each get a key share, like a private key share, and a validation key that would let people validate their partial signatures. And so now, whenever these nodes want to create cryptographically secure randomness, they all sign some common thing, like a communication round number. So let's just say we're on communication round number 42. The nodes all sign the number 42, and they broadcast their partial signatures. And so long as 2/3 of the nodes so long as you recover partial signatures from 2/3 of the nodes, you can make the full combined threshold signature. And the great thing is it doesn't matter which 2/3 of the nodes you get the partial signatures from. Anyway, and then you get this fantastic cryptographically secure shared randomness. And it was funny because I spoke to the cryptographers who created this paper, and they were completely unaware of its application within Byzantine fault tolerance. They just weren't aware of it. And equally, actually, the guy who created the Byzantine fault tolerant algorithm, which used some stuff that I'd derived another algorithm from, he was unaware of its application within cryptocurrencies. And so I think that just illustrates, how much potential there is in combining these different sciences.
So, one big topic in cryptocurrency in general, snarks. Back when I learned about them, and I had a chat with Ali Ben Sasson back in 2013 October. I mean, I immediately really liked the idea. It just seemed so incredibly powerful. I called it a cryptographic God protocol once, basically, because theoretically they allow you to sort of prove almost anything. So, where are they? What's their potential in the near term? What are the obstacles? How can we use them?
Well, in my case, I've been fiddling around with lots of different cryptographic primitives, trying to use them mainly for scalability, actually, because I want to process millions of transactions a second, not just 3, which is the current Bitcoin limit. And I was playing with cryptographic accumulators and non-interactive zero-knowledge proofs. And just recently, I sort of abandoned them all and just gone with generic snarks because it just simplifies things so much. And recently, the library used in the Zero Cash project has been released on GitHub by a guy called Jan Magnuson or something. Some made-up name, anyway. So yeah, the thing with snarks is you can compress the blockchain. So you could have a cryptocurrency that processes millions of transactions a second, and yet you might only have a couple of root hashes in the blockchain itself, in the master consensus log, just a couple of hashes. And yet this thing would be a secure record of millions of transactions being processed a second. And you can push out all of the expensive computation to the clients. And the current system that's available now on GitHub produces these tiny proofs for relatively arbitrary computation, which are only 288 bytes in size. So the existing implementation of the library has a kind of DSL, which means domain-specific language. You can create these kind of circuits from these components it provides you, a bit like Lego. And it's things like, you can perform SHA hashes, you can search a Merkle tree and things like that. And you might, for example, prove that some commitment, which is a thing that contains a coin or something, exists within some Merkle tree. And it might take you, if that Merkle tree, I think is the rough numbers are, if the Merkle tree is 64 levels deep, you might prove the presence of this thing in that tree in about a minute of proving. But this tiny little proof is only 288 bytes, and you can validate that proof in like 6 milliseconds. So especially if you divide up the work, really it's no obstacle to scalability at all. And these things don't even really necessarily, as maybe we'll get to in later panels, necessarily even need to be stored in the blockchain anyway.
Yeah, I think basically using snarks to increase the scalability of the blockchain is a very compelling application. Snarks really enable like very rich applications, and I think maybe the best way for me to do it is to go by examples. So here's one example. So like I mentioned, right, today the blockchain, everything is in public. So every miner can see what goes into the blockchain. Especially, if you have transactions, you have contracts that you run on the blockchain, and everything is in public. But let's say I want to build a crowd, I'm just thinking out loud. Let's say we want to build a crowdfunding application, okay, where people send money to a contract, and let's say after a certain timeout, you see if the money raised has exceeded a certain threshold. And if so, then the crowdfunding has been successful. Okay, so let's say you want to create a crowdfunding application with privacy guarantees, where when people commit money, they don't want to reveal how much they have committed. So perhaps there's incentive to do this because if all the money is in public, once you reach the threshold, maybe no one will be incentivized to invest more. So okay, so how do we create such an application where when people commit money to this contract, you don't see how much they have committed, and then after the certain timeout, you can open the commitment, and then you have verifiability. If I committed $10,000, then I will be basically paying this $10,000 to this contract. Okay, so this is, for instance, one example where you may want to hide the value of the money you are committing to, but you can kind of take it further. So things like zero coin is like, in my mind, is one of the most exciting natural first steps where you want to give anonymity to users. But there's really a lot more to it. Like maybe I want to hide, let's say, what kind of contract I'm running with this other business. So this, and then maybe I'm basically running the secret contract with this other business, and I'm committing some state to the blockchain, and to kind of have intermediate snapshots of this contract, long-running contract. However, let's say if this other party misbehaves, I want to be able to attribute fault and then maybe get my deposit back. So this is also something that zero-knowledge snarks can help. So in general, zero-knowledge snarks is very powerful. Essentially, you can prove almost basically any statement you like in a way such that you can encrypt the inputs to the statement and the outputs of the statement, and then yet you can prove that this certain program was executed on the encrypted inputs to produce this encrypted outputs. So that's the power of snarks, zero-knowledge snarks. Yes.
So, is it possible for you to explain how that works? You don't want to know.
Okay. Is there a short explanation?
I always say it's like but it's nothing. It's not this, but you can think of it a bit like a hash function for computation that you can verify. In that, if this computation is run with certain inputs, it'll always produce this hash function that you can verify is the real hash function. But you don't necessarily, you can verify that hash function, or sorry, the hash digest that's produced, without actually knowing all of the inputs. That's the trick of it. Is that?
Right. So here's my way of looking at how. So let me try to explain one specific instantiation of snarks. It's not necessarily the only instantiation, but this may give you some idea about, in general, how these constructions work. So let's say I have a circuit that I want to verify. The circuit has some inputs, and the circuit has some outputs. Okay, so I want to verify that indeed, I executed the circuit on these inputs to produce these outputs. Okay, so the very nice thing about snark, one very compelling thing is that the verification cost is independent of the size of the circuit. So no matter how expensive your computation is, the verification in some sense can be constant cost. Okay, so how can you do that? This seems like, maybe it seems impossible, right? Okay, and here's the way, one specific construction works. Essentially, you want to check basically, indeed, there's assignment of values to wires such that every gate is correctly evaluated. And if I'm able to check that, then I know the evaluation of the circuit is correct, right? All I have to do is to check that every gate has consistent inputs and outputs. Okay, so the challenge is how to check that in a very succinct manner. It turns out that there's a way to kind of cast these constraints checking into the polynomial world. I can basically express all of the constraints all together using only one polynomial. And namely, it kind of, there's a lot of details I'm skipping, but then essentially, equivalently, I can reduce this to checking a polynomial divisibility problem. And if, let's say, polynomial x times polynomial y equal to polynomial z, then this is an equivalent statement as saying that all of the gates are simultaneously satisfied. Okay, so now with this polynomial, the size of the polynomial is still going to be proportional to the size of the circuit, but there's actually a way to check the polynomial at a random point, in some sense, such that the checking is succinct. Essentially, in order to check this polynomial, you somehow evaluate the polynomial at a random point, and you try to convince yourself that at this random point, indeed, this divisibility check works. So it's a little bit hand-waving, but that's kind of the intuition. Like the key step is where you express all the constraints together as the single polynomial. And despite the fact that the size of the polynomial is proportional to the size of the circuit, checking the polynomial reduces to evaluating the polynomial at a random point. And then it's a divisibility check, right? So let's say P times Q equal to Z. So I just have to show that I know P evaluated at S, this random point, and Q evaluated at this random point S, and Z evaluated at this random point S. So all the work that the verifier is doing is checking, P of S times Q of S is equal to Z of S. But that is not actually done in the clear. It's kind of done in this algebraic construction called bilinear groups. such that in a way that the prover cannot cheat. So yes, so that's a good question. So I've answered how the succinctness can be achieved, but I haven't really answered how the anonymity how the secrecy can be achieved. Well, it turns out that, I mean, to formally prove this requires more work, but it turns out that, so let's say you have a circuit where the input is partly an input, and the other part of the input is a witness. Okay, so what I want to do, the zero-knowledge snark guarantees that the witness is secret. So essentially, when you express, so this witness will also be basically translated into assignment of values to these wires. And in the end, when you reduce that to this polynomial divisibility check, actually those values of those polynomials evaluated at the random point doesn't reveal anything about the inputs. In some sense. It's a little hard to explain that part.
Yeah, I would say that, you know, SNOC, the underlying maths of SNOCs is really, really very complex. I can't even make a claim to understand it properly myself, and I've looked at it. But the good thing is that even in the current implementation, there's a DSL. So you can define the circuit that you want to have executed and later be able to prove the execution of that circuit, right? So from the point of view of a developer, you don't, if you can place your faith in the cryptographers who tell you that the math is sound, you don't have to understand it. You can use it as a technology. You can define the things, that the computation you want to perform. You can define the inputs that you want to be public and the inputs that you want to remain private. And it will generate this circuit for you that you can run. When it runs, it'll prove it at the same time and create this little proof that somebody who holds the verification key can validate. So the use of the SNARKs themselves are very complex cryptography, but they're much simpler to use. And in fact, eventually, you know, you'll be able to take arbitrary C code and turn it into a circuit.
So what would that C code be doing? Is it like doing a coin join with anonymity, or
Well, it's not necessarily a cryptocurrency thing. It's just a cryptographic tool. So if you have arbitrary computation that you want to be able to prove you performed. So for example, I might have a Merkle tree full of hashes, right? And I want to prove to you that I know of a hash in that Merkle tree that satisfies some conditions, right? But I don't want to tell you which hash in that Merkle tree it is. So I could create a circuit that searched the Merkle tree for a hash that met these conditions that I wanted to prove. And when I ran that circuit, I'd create a little proof, a 288-byte proof. And I could give that to you, and you could run it with the verification key, and you could see that indeed I do know of a hash in this Merkle tree that meets my conditions, right? And the conditions might be that this hash is created by combining a random number with a serial number or something like that, right? You could see from this proof that I do indeed know about a hash in this Merkle tree that meets those conditions. But you don't know which hash it is, right? You don't know which hash it is. So you can extrapolate that to Bitcoin, for example, and there might be some outputs on the blockchain, and I want to reuse some output, right? And I don't want you to know which output I'm using because I want to be anonymous. So let's imagine that all the outputs are in a Merkle tree, right? And they're really they're a hash of an address and a serial number or something and a random number, right? And so I'm going to create a new transaction, and I'm going to prove to you that I know of a hash in the Merkle tree. I know of an output in the Merkle tree, right? That has a serial number that I'm going to reveal to you, and it has a balance that I'm going to reveal to you, right? But I don't want to tell you anything else. And so now I've proven that to you. I can reuse that output, and maybe the blockchain records the serial number, so I can't do it again, right? So I can't double spend it, right? But nonetheless, you don't know which output I've reused, you know? It's completely anonymous. So that's a practical application of SNOCs. But it goes far further than that. And eventually, something like Ethereum could possibly generate SNOCs for smart contracts. And people could run these contracts off, on a client, right? And rather than just presenting rather than have the blockchain having to rerun all these transactions to validate that they've been executed, they could just check the proofs, and they could see that these contracts have been executed. So it's by doing this we can offload computation, we can produce anonymity, all kinds of things. It's really powerful. I mean, probably SNOCs are the most. I at least in my rather admittedly humble opinion, I'd probably say SNOCs look like the most sort of powerful piece of crypto that have ever been invented. Is that fair?
I mean, there are other primitives that are also very powerful.